Hello everyone. In the previous video, we have looked at place recognition using vision in mobile robots, which is a very important task. And we have looked at the bag of features, which is basically using localized representations, using features like surf features and so on. In this video, we are going to look at the ones that use global representations of the image. So they look at the entire image instead of only its salient features and removing their spatial information that way. Although here you're going to see that we are not necessarily keeping the spatial information, but we are looking at the entire image. So there are lots of different ways you can do it. The ones that we're going to discuss here is one of them using color histograms, and the other one is using fingerprints that are created by Histogram of Oriented Gradients, or HOG. So first, let's look at histogram. Histogram of what? So there are lots of pieces of information that you can get out of an image, right? One of the most common ones is histogram of color information. So you can use red, green, blue, or you can use HSV intensities if you want. And that way you can look at the entire image. So you go and create histograms from these different channels from all the pixels. And to make sure that this information is not really so sensitive to the change of angle, right, and different view angles, you can use a 360 camera, an omnidirectional camera that gets all of the pictures of the surroundings. So when it turns, it's mostly similar to a simple shift in that image as opposed to complete change of values. So 360 cameras for this kind of place recognition work a lot better than simple cameras with a limited field of view. Now, let's say you got a data set of images, and for each one of them, you found the histograms of RGB and HSV, or individual ones. And let's say you merge them into some big collective histogram, which is all of the 6 channels. And then you find a similar one for the query image. So now what you need to compare is the histogram of the query image, let's say H, and the histogram of an image in the dataset K. How would you compare two histograms? The answer is there are different ways. The one that you see probably a lot in the literature is this guy called the Kullback-Leibler divergence, or KL divergence, which is some formula like this. Now, this is in this case for P and Q, not H and K. Okay, so if you want, you can replace it with H and K here. But the essence, as you can see, is basically a summation over, and this is assuming that these are discrete things. They are histograms. They are not a continuous probability. So summation over individual bins of P in that bin times log of P over Q. And you clearly can see that if the two histograms are identical, then that is going to be log of 1, which is going to be 0. So your measure goes to 0. And if P is not equal to Q, this number is going to be bigger than 0. How much bigger? Depending on how much P and Q histograms are different. Okay, so you can use this. The problem with this KL divergence method is this is not symmetric. So if you calculate dKL of P from Q and you do it for Q from P, these two numbers are not going to be the same. Okay, these are not the same. It's not symmetric. Okay, but if you want to make it symmetric, so here this calculates how much Q is different from P, not really how much these two are different from each other. It's a one-sided kind of thing. If you want to make it symmetric, then you have to basically add these two terms together like this, and then you get to a modified version of that, which is called the Jeffreys divergence. So the Jeffrey divergence, as you can see, is a symmetric one. So D of H and K and H is the same. And you see the formula is very similar, basically. H logarithm, and here it's just 2h over h plus k and 2k over h plus k and times k. So we use this metric here, which is symmetric, and it does a very good job for us. And you're going to see that in the code. Okay, so this is one way to do it. And let me show you the code here. So here, again, I'm using the images in that website that I showed you. Let me show you again here. So I guess it was here, right? That's this link. So all the images are in this website. I downloaded all of them from here, which I showed you in the previous video. So it's appropriate to add that also over here, right? And for my next one, also add it here so you know where these images are coming from. Okay, none of them is mine. So these images we downloaded, and I'm using like 200 of them only for data set and one of them as query. And the number of bins that I'm using per channel in this case is 32 bins. If you want, change it to as many as you want. Given that, for instance, for RGB values, you have 256. So this allows kind of, if you consider it like a uniform distribution, to 8 numbers or 8 sets of values per bin. Okay, but you can change it to anything. Many of the histograms, if you don't give them a number of bins, their default is 10. But you can give it any number that you want. So here is, first it creates this a collection of histograms of all of the reference or data set images. And so you see that it reads the images from the data set and then creates the histogram of the red, green, blue channel, converts it to HSV, then creates the histograms of hue saturation value, then merge them into one giant one and normalize it. So when you normalize, it's good for comparison, and save it, and then does the exact same thing on the query image, and then you use a for loop to compare with the Jeffreys divergence formula. And once you find the minimum difference, that is your best match, and then you're going to show the best match, the query image and their histograms. And when I ran this, you just saw that image, but let me show you again. It's not really a time-consuming operation. Okay, and this is just done with the RGB of the entire image. And you can see that this is my query image, and this is the best match that was found. And again, this guy came from this by some cropping. And you see that they are actually working, although a good portion of the information in this image of the data set is not taken in this query image. But if you look at the combined RGB HSV histogram of the query and the match, you can see that actually they are still quite a bit similar. So it can do a relatively good job if the piece of information that you are missing does not make a huge change in these histograms. Okay, so it is doing the work. Now, it doesn't mean if you try it on each and every one of the images in the database and you manipulate them, you will get similar thing. But you clearly can see that if I rotate these pictures or move them a little bit around, the histograms and the colors still going to be there. So it's quite a bit robust to some of those changes. Okay. Now, of course, if the lighting changes big time, that can change these histograms and you might not get the best effect. But one thing we did to kind of mitigate that a little bit was we did normalization. So that normalization helps a little bit with that. Okay, now that was for histogram of color. What else? Another thing we can do is, as I said, to use fingerprints. What is a fingerprint? So instead of us using the histograms of colors or handcrafted features, which in this case was RGB plus HSV, fingerprints are kind of the way to calculate some compact, low dimension representations of an entire image to represent the image. And many of these are done in typically after some transformation and so on. Like what, for instance? For instance, you can apply some edge detection, right? Or some binary operation or something, get edges that get corners, stuff like that. And then you can use some combination of morphological features like vertical edges, horizontal edges that can represent ground or walls or something like that to represent your image. Or, for instance, if you're using a convolution neural network, you know the different layers of convolution neural network, they are capturing basically different levels of features. The first few layers are starting to get very basic things like edges and so on. And as you go move forward toward the mid and final layers, they capture more of basically higher level features. Okay. So if you want, you can, for instance, grab one of the intermediate or final layers. Okay. And use those as the features to create the fingerprints. Or they can be PCA reduced feature forms or learn embeddings like NetVLAD. Now, I don't want to talk about that because that needs a couple of videos on its own. But basically, any compact representation of the entire image, you can call it the fingerprint, and you can use that. One of the things I want to do here is another histogram as fingerprint, and that is histogram of oriented gradients, or HOG, which is one very common feature descriptor used in computer vision. Okay. And you can use that. Now, why is it different from the bag of features? Because the bag of features was only used on specific surf features of the image, not on the entire image. But this HOG, you apply to the entire image. And you, instead of the entire image and all of those pixel intensities, you just use histogram of oriented gradients, which carries a lot less information than the entire image, and you use that fingerprint as kind of a way to recognize whether it's this place or the picture of another place. So, and again, the reason I picked this, because you can use morphological features, you can use edges or so on. And this is kind of similar to those, but at the same time, since I remember I have not covered this HOG anywhere on my computer vision playlist, I want to explain this and show how to use it for place recognition. So how would you create the histogram of oriented gradients? Why do you call it like that? And how would you create it? How would you use it? The first thing is we don't care about color in HOG. It's about gradients. So all we do is first convert it to grayscale. Then we break down the image into cells, okay? Some small windows, so let's say 8 by 8. So we break the image into this 8 by 8, 16 by 16. That's what hyperparameter that you choose, the size of the cells. And now within each window or cell, we calculate the gradient, the direction and the magnitude for the dominant gradient. Okay, how? Well, you perform derivatives, like you can use Sobel filters or any other filters to, let's say, get an x derivative of the intensities and a y derivative for this. So this gx and gy could be any filter that performs derivative along x and y. Okay, like Sobel filters. If you don't know what they are, go and look at my convolution video. You'll find about them. And once you have these derivatives in the x and y direction, by taking the square root of sum of the squares, you can get the magnitude of the gradient. And by taking arctangent 2 of iy and ix, you can find the angle of, or the direction of the dominant gradient. Okay, yes? So let's say here, for instance, I guess this is like Usain Bolt, right, running, and this is one window around his head, and this is kind of the portion of his head. Now, inside each one of these 8 by 8 cells, you can find a dominant direction and a magnitude for the gradient. So, for instance, at this point is kind of like this, at this point is kind of like this, at this point is kind of like that. And of course, gradient should be normal to the surface, and you see it is. Now, it's not always perfect, okay? Some places it's good. Some places it's not really super meaningful. Some places the gradient is almost zero because it's kind of uniform. But the goal is to find these gradient vectors. Each one has a magnitude and a direction coming from these formulas, okay? And that is kind of like the average for that window, because what you have is you apply a filter to the window and it gives you an ix and iy for that entire window. So you have 8 by 8 numbers for ix, 8 by 8 numbers for iy. So you're going to get 64 numbers for magnitude and angle. So you have to look at either their dominant one or their average one, okay, and place it as a single number for that entire 8 by 8. So let's say on this place here, you say that, well, at this location, row 3, column 4, the magnitude of the gradient is 27 and the direction of it is 39 degrees, okay? And you do the same thing for all of these other cells. Good. Now that you found them, how do you find the histogram of basically oriented gradients, HOG? The way you do it is you go for angles from 0 to 180 and you divide them into so many bins. This number is up to you to decide how many bins you want. So let's say if you say 9 bins, then every 20 degrees you'll go into 1 bin, okay? Or if you want, like, I don't know, 18 bins, and then every 10 degrees will go into 1 bin. So you create a bunch of bins. For instance, something like this. Look here. So here you see that I have basically 10 bins, I guess, right? So 3, 10. So here 10 bins are used between basically 0 to 180, and so it goes basically about every 20 degrees because you also need to include the 0 itself. So you pick a number of bins and you break down the whole range of angle from 0 to 180. You might say, why not 0 to 360? Because this line and this line, you want to consider them the same. You just want the line of action, the direction you don't need to consider in here. Otherwise, you can say that theta and theta plus 180 are 2 different directions. So what you really care about is the line here than the direction. So then what? Then each pixel, or each cell actually here, not each pixel, each cell, that's the correct thing to say, each cell will give you a vote based on its angle and magnitude. How? The direction will tell that the vote goes to which bin, and how much is that vote? Is that like a 1 or 0? No, the vote is based on the magnitude. The magnitude will give the amount of votes. So for instance, let's take a look here. If I look at here, the direction is 80 degrees and the magnitude is 2. What do? I look at this 80, see in which one of these bins it fits in. Well, there is a bin directly for 80, so that magnitude 2 is going to be the vote it casts into that bin. Then I look at this guy here. This direction here is 10. 10 is not exactly one of those, but it fits between 0 and 20. So it should either go to this or to this. So what would you do? You give it to both of them. How? You say the weight of it is 4. I break it into a 2 and 2 and give each one of them the same thing. Now, not always the number that you want is exactly between them. It could be like in the middle. It could be closer to one of them. For instance, look here. You have a 165 with a magnitude of 85. Well, if you look at 165, 165 is between which 2 numbers? Well, it's between 160 and 180, but there is no 180, but instead of 180, you have a 0, which is corresponding to 180. So that 180 here corresponds to 0. So now you have to break that 85 into 2 numbers. One portion of it goes to 160, one portion of it goes to 0. How much does it go to each one? It's based on the difference of 165 to 160 and 180. Okay, because 165 is much closer to 160, so it gives it a bigger weight, and since it's further away from 180, or in this case 0, it gets a smaller weight, and it's linearly proportional. So for instance, this whole range is 20, this distance is 5, so it's like 1/4 from this end, 3/4 from that end. So if you divide this 85 by 4, 3/4 of it goes to here, 1/4 of it goes to there. Okay, so it's a linear interpolation basically that you do, and you assign these votes to these bins, and you do that for each and every one of them, and that's where you get this vector of these bins with some number each. Okay, and that is your histogram of oriented gradients, because they are gradients and they all have orientation and direction. So you make that, and now when you get that histogram, you go ahead and normalize it, because these numbers that you will get, there are going to be all sorts of numbers. They can have fractions, 20, 30, 30.6, 100.5, and so on. So you divide these numbers by summation of them. So now all these numbers are between 0 to 1, and summation of them is equal to 1. So you normalize it. This helps with making it a little bit invariant against lighting changes. Okay, and then you can basically, that histogram is a vector. If you see, it's a vector of a bunch of numbers, so you make it into a bunch of numbers, which is exactly those basically magnitudes of normalized histogram. And now you have a vector that represents the entire image. So now you can compare vector with vector, let's say for instance with the L squared norm. And that is exactly what we are doing in this code here. Again, I'm using those original images, 200. The cell size for me is 64 by 64. You might say, why didn't it go with 8 and 8? Well, I tried that and it did not actually work very well. So one of the important things you have to pay attention to is, if you use HOG, do not use very small cells. Okay? It might make it super sensitive. This is one of the parameters that you can tune, and I messed up with numbers, and I found in this case 64 is actually doing a much better job for me. And of course it makes it much faster as well. So I did it on all of the database on the query image, and then you see here I'm using the toNorm and comparing with the for loop, finding the minimum distance, and finally showing the query image, the best image, and the HOG of the two. Okay, so let's go ahead and run. And this is relatively fast too. Okay, so these two methods are quite a bit faster than the backup features, because they are working globally and they are doing a better job, especially if your cell size is small. And here, look. Again, you see that this, and you see here the image is turned into grayscale, because that's what we care about. So you see again, this query image is exactly matching my best match, and these are the HOGs, by the way, of the query image and the best match. Okay, so these are the histograms of oriented gradients for each one of those 64 by 64 cells. And again, it is working. So hopefully this video was useful to you. We learned two global representation methods for place recognition in this video, and in my previous video I showed you how to use the bag of features and use local features. To get those, I'll give you download link for each and every one of these three codes, so you can play with them and learn from them. Thank you, and I'll see you in the next lecture.